Okay, how this will be the last topic, which will be the eigenvalues of a symmetric matrix are always real. So for this one right now, symmetric matrix, the eigenvalues of a symmetric matrix are always real, considering that a symmetric matrix, matrix A is definitely symmetric if the transpose of A is equals to A. So we wanted to show that all its eigenvalues are real. So there will be a specific um step that we'll be going to follow later on in identifying that one as well, how to do certainly pertains to this one. So whereas this the eigenvalues is definitely the proof that eigenvalues of a symmetric matrix are real. So letting A be an n by n, so it must be a square matrix with eigenvalues that is represented as the lambda and eigenvector as the x. So we'll be going to just check how to do it later on. So given that we're having that there, um, that is specifically what we call this one, there is a uh, a of x is equals to the lambda of x. So that will be the representation, taking the dot product of both side with the x. So just to also um, give you there will be a steps that we will be going to follow as well for this one, since the steps it must the construction for that is not a of x, it must, that is the common, whereas a is the matrix, then you will be, that can be rewritten as well in this formula, so that it would be good. A then could be minus to the lambda, then times to the identity matrix. Then you will multiply that into the x is equals to 0, where your identity matrix will be having the same dimension as your A. So given that you'll be going to have your 2 by 2 matrix, so the 2 by 2 matrix for that, for example, if we're dealing with 2 by 2, it must be like this: 1, 0, and 0, and 1. That is your 1, 1, and your 2, 1. And your 1, 2, and 2, 1 is definitely the same. 1, 1, and 2, 2 is also the same. That is the identity matrix. Um, so that's the equation becomes A minus lambda of I equals to 0 for this. So let me actually give you a specific example for this one, so that we could be able to um, work on this basically. So I'll be going to set a specific example. Let me just go ahead and share this. I'll share my iPad. Okay. So given here, I with your symmetric matrix, you have right now the A, which is the 4, 1 and the 1, 3. So we will be going to check first the eigenvalue equation using the eigenvalue equation earlier, the AX is equals to the lambda of X. Or we can rewrite that in A minus the lambda of identity matrix, then x is equals to 0. So let's actually simplify that first, so that we could able to construct this a minus um, lambda of identity. So how to do it? So we can definitely 4, 1, 1, 3, then minus that into the um we'll be going to minus that into the lambda of identity I. So why is this like this? Because in your lambda, actually, since that is we'll be going to multiply this first. So the lambda of yours, in order for you to achieve the answer for that, you should like let me illustrate that to you for you. It should be like this. So we'll be going to multiply them like that. Then that is equals to the 0. So you will be going to multiply that first before we'll be going to get the determinants for the A minus lambda of identity. So um given that, let me just go ahead and do it for you. So you will multiply that. Suppose it's a scalar, it will be 4, 1, 1, 3, copy as is. Then lambda of um it will become the lambda of times to the 1, it will become the lambda of um become, sorry, my pen is not working. Lambda and 0, 0, and lambda. So that's the um, answer right now. So what we will need to do, perform this already. So for performing that, it will become, so since you minus this one, or deduct that into that particular um, the A as well as your identity lambda. So you will be going to 4 minus lambda, then 1 minus 0 is 1, then 1 minus 0 is 1, then 3 minus lambda. So that will be your answer right now. So for that one, we have to calculate the um, determinant for this. We'll be going to get the determinant for the lambda of, I don't know, the A. This is your answer for the A minus lambda of identity. So now we'll begin to get the determinants for that. So the determinant for this one is definitely 4 minus lambda multiply into the 3 minus lambda, then of course minus 1 times 1, since that is cross multiply as we did. Now we have to simplify that basically. So let me go ahead and it will become um, 4 minus lambda, and then the same thing, 3 minus lambda. We cannot be able to solve that, and then minus 1. So we have to expand our determinant, this one. We can use the FOIL method for that. How we could be able to do it? So first, what will be the first right there? It will be 4 and 3. So expanding that one, it will become 12. Since first, okay, that will become 12. Then, after that one, the outer. So, it will become minus, outer will be 4 and lambda. So, it will become 4 lambda. Then, inside, it will become lambda and 3. So, it will become minus 3 lambda. And after that, the, excuse me, it will be the last. So for the last, it is indeed 2 lambda. So it will become lambda squared. Diba? Is that right? Okay. So for this one here right now, since we were able to multiply already the negative lambda and negative lambda, it should be positive, right? So for that one right there. So take note that it should be plus um lambda squared already, since earlier it is positive and negative, that's why it's minus. So we should be very careful with our identification for that one. Then we'll not be going to include this negative one yet. We'll be going to expand that or simplify, I mean the this one first. So in order for us to go ahead and make sure to segregate those things here. So your 12 minus 4 lambda minus 3 lambda plus the lambda squared, it will be simplified as the lambda squared, then um, minus lambda of 4 and 3, it can be 7 lambda, simplifying each term. So this one plus 12, we'll transfer that here. Since we need to basically um, this one combine each particular term. So we'll be going to minus 1. Thus, your answer right now will become 7 of lambda minus plus 12, 11, excuse me. So that the characteristic equation become right now um, lambda of squared minus 7 lambda plus your 11 then equals 0 already. Now, we can solve that equation. In order for you to solve this, we can solve that with quadratic equation. If you can recall in your high school, that your quadratic expression, we can somewhat use the, if you still remember the negative b, positive and negative, the square root of b squared minus 4ac, then over the 2a. So, where right there, your you will be going to go ahead and simplify that each term, where your um, this will be the negative b will be the negative 7. I'm sorry. Then your a will be 1, then your c will be 11. So a, b, and c. So remember that your a is 1, then your b is 7, c is 11. So we can put that right there. Um, Let me step by step the process. So this is negative b. So our b right now is negative. That is negative actually. Remember. So it will become negative 7. Positive and negative. Then b squared is 7. Negative 7. Negative 7 squared minus 4, then your a is 1, then your c is 11, and your 2a will be 1. So basically, you can now simplify each term. It will become positive 7, positive or negative, negative 7 times negative 7 itself will become positive 49, minus 4 times 1, 1 times 11, we can somewhat um, do it step by step, but Right now, it's okay if you can directly do it. So 1 times 11 equals 11. 11 times 2 equals 44. Okay, that's correct. Then 2 times 1 equals 2. So, therefore, calculating that, 49 minus 44, 7 positive negative will be 5 over 2. So, since we cannot simplify that into the lowest term already, that will be your answer for this equation since we were able to expand the determinant earlier. So, we're able to simplify that into that particular term. So by simplifying the result for the two eigenvalues right now, so you can definitely your eigenvalues of 1 is definitely 7 plus 5 then over 2 and your eigenvalues will be 7 minus over 2. So that's how you will do it for the eigenvalues. How about for eigenvectors?